Hi everyone, I'm Mohammad Khajanejad. I'm going to talk about my joint work with my PhD advisor, Dr. Yang, on H-infinity optimal interval observers for nonlinear systems via mixed monotone decompositions. So I'm now a postdoc at UCSD, but like most of this work was done when I was a PhD student at Arizona State University. Okay, so as you all know, state estimation is very important and critical in many engineering applications where we do need the information about the state of the system, the dynamical system, but we cannot measure the exact true system precisely. So we seek for ways to estimate the state of the system. Traditionally, when uncertainties in the system have stochastic properties, then Kalman filter-based techniques can be used to estimate the state of the system. However, in many applications, information about the distribution of the uncertainties in the system is not available. So in these settings, set valued or set based techniques can be used to estimate the state of the system. And among set based methods, interval based methods are very popular because because they are like intervals are very easy to compute and work with. And so there have been a lot of work on interval observers in the literature for different types of systems, such as LTI systems, linear parameter varying systems, and so on. Some of them need to impose relatively restrictive assumptions on the system to guarantee correctness and stability of the observer simultaneously. And then as alternative ways of getting correct and stable interval observers, people have used time invariant or time varying state transformations so that it makes it easier for them to guarantee stability and correctness. But sometimes these transformations are hard to find like how to as far as my knowledge, it's not really a systematic way of finding such transformation so far. Alternatively, interval arithmetic-based observers have been proposed, and interval arithmetic techniques have been used to find bounds on these bounds over the state of the systems, which can be sometimes very conservative because of wrapping effect. So in this work, we want to consider a very general type of discrete time and continuous time systems with both nonlinear state equation and observation equations, and try to use an alternative bounding techniques instead of interval arithmetic using decomposition functions to design observers which are correct by construction. So to this end, we consider dynamical systems which can be continuous time or discrete time, where X is state. We do have noise, process noise and measurement noise, both both like interval valued noise. And the other important thing is our nonlinear vector fields for both state equation and observation equations have bounded Jacobians, and their bounds are known prehand. So with this setting in hand, we want to design or synthesize correct and input to state stable or ISS interval observers. And by this, I mean, we want to design dynamical systems where the states construct framers for the true system. And by framer, I mean, we want to design X underbar and X upper bar, call them framers, such that the true value of the system, the true value of the state of the system is framed within this X underbar and X upper bar. Moreover, we want that the observer error is uniformly bounded, for sure. And also, we want to have some sense of, or some notion of optimality. And the notion of optimality is like some like H infinity type of optimality in this work. And by that, I mean, we want to guarantee that we minimize the L2 norm of the observer error, the ratio of the L2 norm of the observer error with respect to L2 norm of the augmented noise. We want this ratio to be minimized. Okay, so to design our observer, we use some preliminary tools. The most important of them are decomposition functions. And we do need decomposition functions for both discrete time and continuous time cases. So to briefly introduce decomposition function, given a discrete time system with a vector field F, we call FD, which is a function over the high the domain, which is z times z. So z is the domain of F. So the domain of FD is z times z. FD is defined over z times z, and FD has three conditions. So FD of z and z coincide with f of z. FD is monotonically increasing in its first argument and monotonically decreasing on its second argument. So this is for discrete time systems. For continuous time case is almost the same, with the subtle difference that all these monotonicity things should hold only over off-diagonal arguments. Okay, so this is a definition of decomposition function. The nice thing is, if you have an n-dimensional dynamical system, and if you can find these decomposition functions for them, then we can build an embedding system. An embedding system is this system 2, is a 2 n-dimensional system where like this FD of under the lower values of state and noise and upper values of state and noise construct the lower framers, and FT of upper values of state and noise, and lower values of state and noise construct the upper framers. And then it is proven that if such an embedding system can be constructed, then the true state of the original system is embedded or is framed within the states of this embedding system. Okay, the next important concept in this work is Jacobian sign stability. So technically, mapping mu is Jacobian sign stable if its Jacobian matrix argument doesn't change sign on its domain. So the arguments of the Jacobian matrix of this mu over the whole domain either remain positive or remain negative. Okay, now the nice thing is, for a function f with bounded Jacobians, we can always decompose this f over its domain into two components, a linear component or function, and a Jacobian sign stable function. And this decomposition is not unique. We can do it in multiple ways. Moreover, this Jacobian sign stable component admits a decomposition function which is tight. And also the difference between upper and lower values of this decomposition function over any box or interval is upper bounded by an affine function of the diagonal of that box. All right, with these tools, now what's our strategy to design an observer? So the first step is to just do this Jacobian sign stable decomposition over both state equation and observation equation. And then by doing this and adding this kind of feedback term with L being the observer gain, we can decompose the state equation into two components, a linear function over state and noise, and a nonlinear system or function over state and noise. This is the beginning step. And then by doing this, this is again what the summary of what I just said. And then after doing this, we compute linear embedding systems for this linear component using all those techniques, all those preliminary material that I just described. And then you can see that there are slight differences between continuous time and discrete time, and this difference originates from the fact that decomposition functions are slightly different for continuous time and discrete time. And also we do the same thing. We find nonlinear embedding system for this nonlinear component of the state equation, again using decomposition functions. And then we just combine these two steps by adding up these linear and nonlinear embedding systems. And by doing this, we get an embedding system G hat for the original system, which is like this. And then as I described before, using embedding system from mixed monotonicity literature, we show that the error system here is positive or cooperative by construction. And this equivalently means that the observer is correct or the true state is within this upper framer and lower frame. Okay, this was for correctness. The next main result is that like when applying some LMI methods on this error system, we can derive a semi-definite programs with LMI conditions, which if we solve, then the solution results H infinity optimal observer gains for our system, for CT case and DT case separately. And this guarantees, this sufficient condition guarantees that the design interval observer is both input to state stable and optimal in the sense of H infinity. So after designing this, certainly applied it on some benchmark system, first continuous time system, and then we compared our observer with some like benchmark observer in this reference. And as you can see, the red lines are our framers, are certainly like tighter than the blue lines, which are the framers from this like DMN reference. And from the beginning, in the beginning, ours is certainly tighter, and then as time increases, they get very close to each other. And then the error also, the beginning our error is pretty much lower, and then when time goes, the errors are very like comparable together. Also, in the discrete time, we compared our approach with some approach, like with some very recent interval observer design in this work, Tahir and Echikmese 2021. And then it can be seen that ours is definitely tighter, like this red line and magenta line show our framers compared to these blue and black dots, which are from this Tahir and Echikmese paper. And also the error plot clearly shows that our errors are lower than theirs. Okay, with this, I'm going to conclude that we proposed a unified H-infinity optimal interval observer design for locally Lipschitz nonlinear continuous time and discrete time systems with nonlinear observations. We leveraged mixed monotone decomposition functions to design correct by construction framers. We do not need to impose any restrictive assumptions such as global Lipschitz continuity or contraction to design our observers. We provided sufficient LMI conditions for stability and optimality. And in future, we want to extend our work to design state and input observers, and also we want to work on designing interval observers for hybrid systems. So here is a list of some of the references that have been used in this work. And with this, I'm going to thank you so much, and I'll be happy to take any questions you may have.